Today's speaker is Tom Collopy from Qualcomm. Tom's worked in the area of embedded microprocessor design and software design for quite a while now. Long time. And he's now leading up one of the software groups at Qualcomm here in here. Tom's going to talk to us about wireless devices, mobile device challenges.
Does this end right at 3:10, or can we kind of slide a little
You
bit?
can go a little long.
Okay.
You'll be all right.
All right. So if you could do me a favor, take out anything that's in your pocket that's electronic. Put it on the desk. Anything. So, someone raise their hand, tell me what they love about what's sitting in front of them. They just love it. It works.
It's red.
Got two. What is it, 30 people in here?
Little.
Everybody raise their hand who has something they hate about it. Looks like the hates win. I suspect that when I get done with this, I'll probably maybe either said your hate directly, or I've touched on your hate. And we'll do a test at the end. That'll be a test of whether I did my job or not, whether I can understand your hate. Okay. And then it's going to be your job to fix that over the next 10 years. So what we think is happening, what is happening, everybody thinks is happening. Devices are converging. So my device doesn't look like a lot of your guys, because you got laptops, you don't need one of these. I travel a lot. It's a little computer and a phone that we got. Win Mobile, so it doesn't have a blue screen of death, it just hangs. But I can read my email, my calendar's here. It's the same email and calendar I have on my laptop with my business stuff. If I need to, I can view a PowerPoint file or a Word document. I use this to do email when I'm traveling. I use this to keep track of where I'm supposed to be. It tells me, hey stupid, go to NC State. And it also is my phone. It's got a little keypad down here that I can use as a phone. And I got to unlock it. Call Mike Matt, mobile. No. Cancel. And I can talk to it through dial. I have about 1,800 contacts in this phone. Now this is 1,800 I've collected since 1983 when I started in the embedded business. And I've dealt with a lot of different people because I not only manage engineers and have done engineering, but I also partner with other companies and negotiate agreements. So I come in contact with a lot of people. I cannot scroll through 1,800 contacts to find somebody. Like Matt, I call at least 3 times a week. Most convenient feature I have on this phone. But this phone fits me pretty well. This phone, none of you have this phone, I don't think. It's an i760 Samsung phone. If you started calling out the names of the manufacturers of your phone and what you use it for, you'd probably get a very wide selection of things. Different manufacturers, different service providers. I think that sort of looks like an iPhone, might be a touch iPhone. It looks sort of like a BlackBerry or a Treo. So that looks like something different up there. Yep. Those are just straight phones. So different strokes for different folks. It's like shoes in an airport. Walk through an airport, see what kind of different shoes. Different people want different things from their mobile devices. They want computing, communications, information, entertainment, interactive communications, social networking, new buzzword, mobile communications, information, entertainment, communications. It's happening in both computing and mobile communications. These things are coming together. This is a mobile computer and communications combined. The form factor is great for one reason only. It's because it's in my pocket. But the screen size isn't the perfect screen size to browse the web. It's probably that Lenovo that you're using right now, or something in between. So people want a lot of different things, and they want it their way, and they want it all the time. So you've got a bunch of different form factors today because people want to do different things. thing that's most important to me is not the thing that's most important to you, so your form factor is probably going to be different from mine. You may hate when Microsoft, so you want to get a Linux phone. I bow to Microsoft because they give me my email, my calendar at work. So there's a lot of different things that people want, different form factors, but there's some things that are common. And if you look at the history of computing over time, in phones, 2.5 megahertz, Intel, you guys will know what this is, 8186, 10 MIPS machine. He knows. He probably knows. I know Conti knows. He's older than me. 20 MIPS, 1998. I mean, that wasn't that long ago. You guys were, you were in high school. 27 megahertz, 23 MIPS. Not much happened for the first few years of cell phones. And then this word multimedia started coming into play. More visual, more audio, and 40 MIPS. ARM started taking their place in the mobile space. Next platform after that, 250 MIPS of 225 megahertz processor. This was a big jump. A lot of engineering work. A lot of things tried for the first time. Not all of it was done right. Then, when I joined Qualcomm, they were doing this. So I joined Qualcomm in 2003. And this device has 2 ARM processors, 2 DSPs, and a bunch of coprocessors, and a bunch of communications and I/O. And these are just starting to come out in phones today. And then that thing up there is what I joined Qualcomm to help bring to the world, and that's a Scorpion processor that's a 1 gigahertz processor. 2.5 megahertz, 1996, 1 gigahertz, 2007. Big, big jump. That's a computer as much as, an 8. This is a 1 gigahertz low-end Intel computing platform. So, same thing. What's driving all this? Power consumption's going down. I don't need a big clunking battery to drive a gigahertz processor anymore. And the device size is getting smaller. It used to be that to put a gigahertz processor in a box, the box had to at least be this big and that thick so that you could power it for 2.5 hours. And now you got a gigahertz and something, the next devices will have gigahertz in this size. So a lot of things go on. Lower power, high integration, and lower cost of silicon to create these devices doing computing. So what do the devices of tomorrow possibly look like? Well, I too would like multiple devices. There's times when I would want a really thin, simple phone that I can't even feel in my pocket. Maybe it sits in my wallet, and I can put a little clip on, and I can just talk to it. It's like call Mike Matt Mobile, and it's like the size of maybe that many credit cards. That'd be pretty cool. If I could slide that into a case that then was my iPod player, and all my iPod data was on this electronic device, then I could just do my iPod stuff. And then when I went on my business trip, I'd slide it into this case, and all my data would be there. And then when I needed to edit the PowerPoint for this presentation, I'd plug it into a laptop shell, and all the data would be there. So morphing screens, morphing the user interface to what consumers want, that's what we'll all have to be doing. And having the computing power in an efficient design is what is the problem that we're talking about today. So, what are key features? It needs to turn on right away. Biggest thing I hate about there's a long list, but one of the biggest things I hate about a laptop is I open it up, and I travel a lot, so plane lands, I sit down in the terminal, I've got half an hour to reconnect, get all my email so I can do another batch of email when I get on the plane. First 5 minutes of the thing booting up, the next 2 minutes of reconnecting to the network. That takes a lot of time. That's, for me, 7 minutes is probably 20 emails, because I get 160 emails a day. So, instant on, always connected. I don't want to have to open it up and connect it. I want it to start connecting as soon as the pilot tells me I can turn the thing on. So by the time I sit down, all my emails are already there. That's what this phone does for me. Long battery life. Laptop today, 2.5 hours, and I got batteries all over the place in my laptop. 2.5 hours. My plane flight to Dallas is 2.5 hours. My plane flight to Seattle is another 2.5 hours. If I don't have a charger, which weighs about 5 pounds, then I can't make it to San Diego and do work for 5 hours. I can only do it halfway. So battery life. Sometimes my battery runs out. I can't plug it in to charge it in the plane, so I do email on this while I'm on the plane. All my data all the time I talked about, highly portable. The biggest thing people like is putting it somewhere that's inconspicuous. But the other contrasting thing is they want a human user interface that matches the application. So if you're browsing the web, you'd like a big screen. It's hard to put a big screen in your pocket. So there's a lot of mechanical challenges, and I want to be able to have every application anywhere all the time. So if I'm in a new city, I want this to be my GPS device so I can find my way around. If I'm blocked from cellular because I'm in the bowels of a building, there's Wi-Fi, I want it to do Wi-Fi. I want it to pick the connectivity that's the cheapest, the easiest, and the fastest to give you my information anywhere, anytime. And if you look at these different devices, they're different form factors. Laptop, something about this big that has a bigger screen, so the browsing the web is better. This is actually a poor image, but it's a gaming device, so it's got what you'd want to have as an interface for gaming. Another attempt at a laptop, small laptop, iPhone, multimedia player, and a phone. Very different form factors, but these features are common typically to all of us. So what are some of the big ones? Battery life. This is where people, when you talk to people, they'd like to see the battery life. I like my laptop to last all day. From the time I wake up in the morning to the time I plug it in at night, I'd like my laptop to last that long. And I want the screen to be at least 7 inches big. For a device that is my portable media player, browser, 2 or 3 days. I want to take it on a trip and not have to worry about plugging it in every night. For media players of other types, I want to go about a week, and for my phone, I don't ever want to think about it. I just want it to work all the time. The screen size tends to go as the battery life. Screen size also tends to go as ease of use and the how you're going to carry it. If I've got a purse or a briefcase or a backpack, I can typically get either a small finger keyboard or a laptop form factor. As I go smaller, there tends to be a transition from a keyboard that your fingers fit on nicely to your thumbs, and usually nothing in between. In Asia, they have smaller computers. The pitch of the keyboards is smaller. People here tend not to like to use them because it feels like you're doing this. And so the form factor is changing depending on where you're going to carry it and whether you need a keyboard or not. And then, what's happening related to power? Power goes up with screen size. It goes up typically with computing demands. It's the amount of energy you have in your battery goes down the smaller the device is. And if you look at power in an audio system, let's say you're trying to do an MP3 player on a phone or an iPod, the people that let's say you go work for a company that does, that makes chips to go into iPods. I bet you every day someone's going to be asking you a power-related question because the people you're competing with are getting better all the time. This is 2006, 4 different phones. The number of hours of playback on each of those different phones. If you were a consumer interested in playing audio like on your phone and you got those 4 different options, he wins. He might sell some, these guys lose. You're not going to buy the product. So power would be a key differentiating factor. How much power you burn in your design will decide whether or not your product survives and probably your job survives in this mobile marketplace. And the guys that are doing power in 2008, they're looking at 10 milliamps, burning 10 milliamps of power with a screen of an iPod being up and running and all the electronics doing all it has to do, 10 milliamps is what they're burning in 2008. And in 2010, it's going to be a fraction of that number. And it goes, it's not a simple equation of how you, well, I'm just going to do A or B or C. When we do power analysis in our designs, it's the clocks that control the logic. It's the software, and whether that software stores stuff in external memory or internal memory on the chip, because I/O burns more power than non-I/O transactions. It's whether we use a 1 gigahertz processor or a 200 MIPS processor to do that computing. It's the bus. Is the bus turned on all the time? The bus that's communicating across those cores burns power. So if you leave the bus running when there's no transactions, you're burning power. It's like a Colombo mystery. You guys remember Colombo? He was an investigator. He would look and look and look and look until he found the guilty guy.
Yeah, you are old.
He just keep digging and digging and digging and digging until he found the guilty person, right? And the evidence was, little tidbits of evidence everywhere. That's what reducing power is in today's devices. It's not like, oh yeah, I can just cut it in half by doing one thing, and I can double the use. It's everywhere in the design. It's the battery design, it's the charger design, it's the PIMIC design, the power management IC, it's the communications chips, it's when you turn things on, when you turn them off, what the backlight is on the display, how big a display it is. It's everywhere. And it's little bits everywhere. We had a problem in Qualcomm with battery life playing an audio clip. Ours wasn't competitive, right? The solutions our customers made weren't competitive. There were 15 things that changed in probably 4 different disciplines, and we got a 2.5x reduction in power. But it was 15 different things that we had to do. It was a little bit here, a little bit there, a little bit there, changed the way the software worked. Yeah?
How much of that application depend?
The number of things that you would touch or go look at is, you go look at everything, quickly reduce it to a set of probably 10 to 15 items, and that set might change by 2 or 3 for every application. If you're playing video, you're doing a lot more computing. If you're doing audio, you're not doing really a lot of computing. So in video, you're looking more at the computation. In audio, you're looking more at everything in the system. The power driver for the mic or the speaker, the PIMIC everywhere. So you'd start looking in the same places for every application, but you'd quickly understand, okay, this is more of a computing application. I need to be more efficient computing-wise. This is more memory, transaction intensive. I need to look there more. So it depends on the application in that way. If it's screen related, screen manipulations, 3D user interfaces, computing, and the display would be places you go look. But you kind of end up getting a list of 30 suspects that typically you work with, and then at 30, you might have 15 different ones for video, and 12 of those are the same for audio. The compute one's different, or the memory's different. So this is the good news after we figured it out. 80 plus hours of music playback. So this is in a 600 megahertz ARM11 chip. It runs 3 different types of operating systems. It's a 45 nanometer design. It's got 2 and 3D graphics acceleration, GPS, FM radio, plus a whole collection of other communications interfaces. The ARM11 is not running at 600 megahertz, and it's not doing the audio processing. That burns too much power. There's an ARM9 in there, and there's a small DSP, and the DSP is the thing that's actually doing the computing. It's a very small, efficient DSP. And so these are the kinds of times that people expect today in a chip that goes out the door in a product, and those numbers keep going up and up and up and up. Longer, 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 with smaller and smaller batteries for thinner and thinner devices. Kind of applications people want to do. Talked a little bit about this before. I would guess that, well, in each of those 6 major categories. Does anyone say that they wouldn't want one of those categories? You're going to browse the web, you're going to send an email to somebody, you're going to play a video. Most people like to play games that kill time or enjoyment, find out where you are and talk to other people. And half of those on the top were all computing kind of applications just a few years ago. And so, what do people want? So you're going to be, just got over from the College of Design or Industrial Design. They're looking at it from making things easy to use. They would be coming to you saying, hey, I got this cool idea for the iPhone killer. It's going to be better than the iPhone. It's going to be thinner, lighter, easier to use. And you're going to go to them and say, but I can't make it that small. I can't make it that thin. I can't make it that light. Why do you want to make an iPhone killer? Why not make a thing with a keyboard? That's better. More people will buy the thing with the keyboard. But what this chart shows is talking to 5 different groups of people. So this would be people your age group from a consumer perspective, people that are more my age group, and people that are more my grandparents. Those 3 age groups. And then 2 categories, consumer users and business users. That's the 5 different groups. And they said, we went out and studied these different groups. We said, here's these different devices that are on the market today. Which one do you like the best? Well, group 4 and group 2 like this thing that was a small keyboard the best. Group 1, 3, and 5 liked the iPhone, but group 2 didn't like it so much. Group 2 liked this more keyboardy thing better. The point of this chart is different people like different uses depending on how old they are, what sex they are, whether it's business, whether it's consumer. There's no one size fits all. And so when you take into account, when you're designing a chip for this mobile marketplace, if you think, oh, it's just going to be a phone chip, so I don't have to do this, this, and this, that's going to limit your market for that design. On the other hand, the more things, the more general you make that design, the harder it is to make it very power efficient, because you're going to need a bigger processor to do the computing side of it. But that's going to burn more power. So you're going to see in mobile design a lot of different form factors that people are going to want. It's very personal what you're going to ask for from your, when you go buy something, and that's what people are going to say. And we were surprised that there were not more devices that people said it's the best possible device ever. I mean, these 2 devices probably came out ahead of anything. They're more different than you can imagine. Right? So that's what people want. Now, how much would they pay for something, and what would they be likely to use? So this was one of those segments that I talked about of the age group and consumer or business. And this particular segment said they'd be willing to pay the most for things on the right-hand side, and they're most likely to use the things that are up above. So this device, turns out, of everything that's on here, probably costs the most of all these, and they hated it. This is what's called the UMPC. It's to Microsoft standards, and it's heavy, hot, and very difficult to use. The other thing on the other side is also to a Microsoft standard. It's a laptop. It's heavy, and it's hot, and it's difficult to use. It's the form factor that's the only difference. It's kind of bizarre. The price is about the same. And people thought that by making that thing mobile and not having to deal with a keyboard would sell more. These things don't sell hardly at all. A couple 100,000 units a year. It's the things that can fit in your pocket that tend to be in that, yeah, I'd probably buy it if it fit the right price. That's the things that tend to sell the most. So, what drives performance in the devices? Fancier user interfaces. The iPhone is going to employ a lot of engineers for the next few years. Not necessarily at Apple, but all of Apple's competitors. Because Apple set a different standard, right? cooler user interface, multi-touch screen. It just, yeah, especially if you're in software. The software of these other devices is clunky compared to what you see. So 3D user interfaces, productivity, multimedia. Productivity if you're a business dude, multimedia if you're a consumer, no matter what age group. No matter what age group, people like to listen to music and they like to watch videos. Video editing and speech to text. We like to put those up there because they drive a lot of computing MIPS, but not too many people are thinking of doing video editing on a device that they carry in their pocket. Speech to text, however, I call what I just did with Like Matt Mobile as speech to text, but it's for a specific application. Browsing. If you want to go get a job at Apple, Samsung, anybody else that makes devices where there's a browser involved, and you understand, if you're a hardware guy who understands what browsers do to the hardware in terms of power and performance, or you're a software person who understands what your software does to the hardware in terms of power and performance, you can probably go get a job tomorrow. The browser is the one application that spans almost every one of the devices that I showed you. It's an ugly application. It's big, it's huge, there's a lot of code. It was written by a bunch of different people. No one ever conceived of it going into a phone. No one ever conceived of, when they wrote that code, that it needed to be in a battery that lasted a week. And so the browser, if you're thinking of an application to do a project with, or you're thinking, which piece of software do I focus on, the browser is the one. Because it's ugly, causes a lot of power to be burned, puts a lot of stress on the computing side, the bus, the memory controller. It's typically you're connected through a communications channel when you're using it. So that's the hot one of the day, is browsing. User interfaces. A lot of touching, panning, scrolling, zooming. That takes a lot of software. People are now, Google is into web top applications where if you get to the web, that's how you get to your application. You don't buy Microsoft anymore. This will be a lot of computing cycles, more advanced 3D games. In the chip that we're doing now, we call it Snapdragon. We've got a downsized version of a graphics core that's in the Xbox 360. It's going to go in phones. That's a lot of computing power to add to a gigahertz processor, a 600 megahertz DSP, and a 250 megahertz ARM, and a 250 megahertz another DSP. A lot of computing power in there. Making it power efficient is the only way you're going to be able to play games for 2 or 3 hours at a time with that much computing going on. And then advanced navigation and mapping. We'll talk a little bit more about that in a minute. So, you're thinking, great, I'm going to be an expert on power. It's going to be easy. I'll just learn about, P equals I squared V, or what B squared, or whatever that. I got the equation, I'm going to be an expert. And then you get to your job, and let's say you're the person working on power management. So, go to the customer says, I got 17 things that you need to do for me for power management. It's going to take you all day. Let's say it's the PIMIC design. It's going to take you all day just to figure out what you've got to do for that customer. Power is going to be, when people are talking to you, like an unspoken thing you've got to go do. It's not like they're going to hit you upside the head and say, for your audio driver that you're writing, you need to have only this much current flowing while your audio driver is working. It's something that you've got to do yourself. It's not something that is part of the specifications. There's probably 100 specifications there. None of them will say power. Okay? And then when you go to work on trying to optimize your power, there'll be a bunch of standards that other people have set that say you have to decode real a certain way or Windows Media a certain way. And you say, well, I can make it more power efficient if. And that's not going to, it's going to be a constraint. So there's going to be a lot of constraints that you'll run into when you're looking at trying to build an efficient design. And then here's this location-based services. It's one that people tend not to use, but I think could actually be pretty cool. Knowing where you are, or if someone knows where you are, you get in a crash, press the button, and they come find you. What's around me? Where are my kids? Yeah, you don't have that problem yet. Being able to pay without having my wallet. I'd love to get rid of that thing and just walk around with this, as long as I knew that no one was going to rip me off. And it worked all the time. Gaming, we talked about, and where's my buddy? If this stuff works seamlessly, you could do it all the time, it was very power efficient, didn't drain the battery, you'd probably do this stuff. But you've got to be sort of like us to make it work. And most of us probably don't spend the time to do it, even as engineers. Now, small matters as well. This is the collection of silicon that makes a laptop work. It takes up a lot of space. The smallest they've been able to make the content of a laptop is a brick about 4 by 6 and maybe 3/4 of an inch thick. That's the smallest they've been able to make it, and still be able to dissipate the heat, have enough battery power for it to last 3 hours. This is what we're working over in Qualcomm on. So we've got the silicon today. People are designing it in today. This is about, I think it's about 300 millimeters cubed volume-wise. I think that's 3,000. So a huge difference, just from an engineering point of view in terms of volume. Power and volume tend to strangely go together. The smaller you make it, the more efficient you make it. The less silicon you use tends to mean you're going to burn less power. So when you think that Intel's going to rule the cell phone world, just keep this image in mind. They got a long way to go. So a little ad for Qualcomm. Snapdragon's what we're working on. Snapdragon. This is my boss's boss's boss. Extremely bright person. Probably the smartest person I've ever met in my whole life. And so there's a lot of investment that he decided to make. He's the guy who said in one meeting before he hired us, show me some lead. What are you really going to bring to Qualcomm? And we claimed we were going to bring this low power 1 gigahertz processor that's going to open up new markets for him. And that's where we are today. We have customers designing us in 3 years, almost 5 years after we started. He spent a pile of money on us because we were going to be able to help him go after this market. So it's a big deal from a business point of view to make low power, efficient designs. It'll win customers. So what's it all mean? You need expertise in more than just your area to understand how power is affected and how what will work in influencing power and what won't, size, thermal issues, process technology, system analysis. I tell you, the thing that's hardest for us to find is someone who understands the whole system enough to make a trade-off between should we put the code in this gigahertz processor or this DSP, or is it more efficient to design a hardware accelerator? How much traffic is going to be going on that memory system? Understanding the software enough to know what the traffic is going to be in the hardware, those are the hardest people to find. And if they understand power and that, they're like gold. Okay? Challenge is, you can put all this stuff on a piece of silicon, but how do you get it designed quickly and efficiently? And there's going to be many different kinds of devices, because there's a big trade-off amongst all these different things, and all these different disciplines go into making it. But if you have it, I'd love for this phone to look cooler, be half the size and half the weight, and last twice as long. If you could design that, I'd buy it. I spent, well, my company spent about $400 on this phone. Okay. So it's an important thing to any business in the mobile market. Any questions?
This is in continuation of that discussion you had about, you said you had to change 15 different things to make a 2.5x reduction in your power. So how does that tie up with your aim of doing, or you want to have a comparable device, right? So you can't really do that in real time, can you?
Do which?
Morph your requirement.
Well, what actually happens is the device, Snapdragon is a device about 100 square millimeters. It's got many different components in it that have all kinds of settings in it. So an engineer sits down and says, in my memory controller, you can control 25 different things. He's done it for a long time. He understands that. He's been thinking about power. The bus person designs it so you can tweak 25 different things. The processor guys say you can set the cache this way or that way. Okay. Now, someone comes to write software, doesn't really understand all 25 things in the memory controller, the bus, or the processor. And there's different ways you can implement the algorithm. Let's use video decode, for example. You can use the neon accelerator in Scorpion. You can, where you put the data will control part of how you do the power. So even though you have a fixed set of hardware function that different people have thought different things about, you can still go in after the fact and say, they didn't think about this, they didn't think about that, they didn't think about this. And that's really what we do. So turn this, we're not using this logic, turn it off. The PLL, these 3 PLLs can be turned off. We can use this 1 PLL. We can turn the clocks off on the bus for this period of time. We can, when we're doing this audio algorithm, we can turn the CPU down to 0. We can use the DSP. We thought we were going to use the CPU. We can move the data onto onboard stacked memory as opposed to off-board DRAM. And those are the 25 things you do after the fact. The things you do before the fact are making sure you got clock gating in the design so that people can turn things off. When you look at the algorithms, you look at what's the most efficient compute engine for the level of computing you need to do. So you don't make the assumption because I'm a C programmer and I like general purpose CPUs that my DSP, or my algorithm should naturally go in the CPU. Maybe the DSP is the right place for it to go. And so there's stuff that you have to think about beforehand, but there's even a lot to be mined after the fact. That 2.5x was all after the fact. Now based on what we learned in that, doing that 2.5x, there's another 4x that we said, if we could change this in the hardware and do it that way, then we can get the 4x. And so the next generation, you do the 4x on. And it will just repeat. When we do the next piece of hardware, people are going to come up and say, but if you'd have thought of this, and you just get smarter and smarter and smarter at it. I'll let you ignore them. Yes?
So is there a specialized compiler to take care of all these hardware microarchitectural parameters that can be controlled, or is that not a big deal in this industry?
He believes you can do that. I'll pay a lot of money when he gets one that can. No. So,
Because people normally will not be compiling their own code on phones, right? So is that not a big deal?
it's one of the 50 things. So you want the compiler to do its best possible job, but in some applications, the application is only going to run for 3 seconds a day, but you want to run it as fast as humanly possible. So the compiler settings for that person are give you the maximum performance. Then you've got this audio engine that says, I don't want to write the whole thing in assembler language. Let me write some of it in C. So, but I want to compile it so it gives me the most efficiency, the most compute for the milliwatt. And then I can turn it off. So it might be that you compute very quickly for a short time and stay off, or you compute a little bit for a long time. And different computing engines are better at different ones of those. So people trying to put energy as one of the parameters into a compiler option, it's not very sophisticated at this point in the level of capabilities. So if you had smart ideas in compilation that were automagic to the user, flag says optimize for power, press the button, you got the better power code, then people would 1,000 people in Qualcomm would use it. If it said, you've got to set 17 compiler flags a certain way, 7 guys in Qualcomm. Those 7 guys may not be the right 7 guys to optimize the right application. So simplicity in compilers is important because there's a lot of people writing the software that goes into a single device.
So in a sense, there's a specialized compiler for every single component that you're going into the phone? I mean, so take browsing, for example, right? You said browsing is one of the most power-hungry applications throughout the different platforms. There are people who are currently trying to make GPUs, graphical processors, work for general purpose algorithms, GPUs, but it's very difficult. It's very unnatural to fit a browsing application into what the compiler for the GPU uses.
Right.
So, in a sense, are you talking about sort of a motherlode compiler sitting up top, controlling a whole bunch of compilers down in the hierarchy for each one of these specific accelerators, DSPs, etc.?
From a practical company the size of Qualcomm software development perspective, that would never apply. But if you had a compiler that had intelligence to say, if you could give it the parameters of the different compute engines that you have, and you said, take this C code, or C++ code, because that's the simplest, most common form of code from an engineering point of view, compile it for these different engines, and figure out which one of these engines is the most efficient. That would be much more than we have today. What we have today is 5 different compilers for 5 different compute engines. And those compilers, we're just now getting to where the DSP takes C code as a compilation. And so that's a big step forward to be able to say, compile it on the DSP, compile it on the general purpose CPU that we have, and see who wins. But the see who wins part still takes, I've got to go in and optimize this, and this routines to really get the best power. Just straight compilation doesn't do it.
So you mentioned that you change something because of power improvement. I'm just curious, how do you actually estimate to get this number? Do you actually do measurement? I mean, probably it's too late, right? Because
So the example I gave you was an after the fact example. That was an example of when we first came up with the design. We had some power targets. Some people had some, but typically, because we're Qualcomm, they were modem related, talk time, standby time, because that were the most important parameters in selling our devices to people. We designed the device. It had enough computing power to do audio processing. Audio processing really wasn't a big deal in phones when that design was going on. So after, in the case of the one I just showed you, it was after the fact, 15 engineers from 15 different groups got together and said, okay, we've got to cut, we've got to increase that audio playback time from the 30 hours to 80 hours. And so it wasn't after the fact, what can we do to the hardware and the software in all these different areas to solve the problem? Now we're trying to get smarter about it and say, before we even design it, where are we going to allocate the power in the system to get to a certain amount of current and milliwatts for audio playback? So the CPU gets this much, the bus gets this much, the memory gets this much, PLLs get this much, the communications gets this much. You now try and set targets that you think are close to what's going to deliver that other number. The targets are good because it makes engineers focus on the power stuff. They do the design, the guys write the software, you're way off. Because the software guy threw the software together, got the product out the door. But then you go back and they start looking for, okay, how do I get the software written that really makes best use of the hardware as it was designed? And then you bring it down and you get close to that original target that you set. So we're just now getting to where we've gone through it enough to get reasonable estimates and then go do the design and then go do the implementation and test it to see if it matches what we estimate.
another question is, how much do you think you can integrate both analog and digital together, or actually they still cannot different work?
There is a mixture of analog and digital on the digital die that we have for Snapdragon. It's limited. There are a couple of things that limit it. RF technologies usually are multiple generations behind. If you try and implement those analog technologies in a digital system, you may add multiple layers to the digital portion, which raises the cost. So it's not that people don't know how to do it, it's more of a cost issue. And there's also an issue of how quickly do things change. So if you have a design that, an analog design is very complicated to do, and there's some black magic in the analog design, and you get it right. Now you never want to touch that thing again. This digital design, we're pumping out new designs start a new design every 9 months. And we're relaying out that chip to make it as small as possible. And so the layout changes all the time. So you either have this big hunk of big component analog stuff that stays the same and you're trying to design around it, or you put that on a cheaper technology, older technology, leave it alone, and then you make this digital stuff as efficient as possible. So there's a lot of trade-offs. It can be done. It's done judiciously in our designs, and there's parts that we don't do. The PIMIC stuff is a separate chip. The RF is a separate chip. We do single chip designs, which are, single chip's kind of a misnomer, but it's integrating more of the RF, analog, and digital together. But those tend to be for the simpler, smaller designs.
So why does all this computing have to happen on the phone? Why can't I just have the computing happen somewhere else and give me the result?
So, I'll go back. Tom will know this. Back in the old days, good or bad, the computing was done somewhere else, and the image was rendered on your screen. Mainframe computing. That's where I started. I came into engineering just as the first PCs were coming on board, and I fell in love with PCs from a schematic capture point of view. I was doing printed circuit board design stuff. I had complete control. Nothing ever got lost unless I lost it. It was always there. So I could work even if my connection was to the mainframe was down. And I think that the same thing is still true. I want to be able to work no matter where I am, whether I've got a connection or not. I may be more effective if I've got a connection. But if I'm on an airplane right now, I can't work. I need to work for 5 hours when I'm on an airplane, because that's what it takes to get to San Diego. So personally, I'm not a person that believes in that model for the bulk of my applications. This concept that Google has of their apps, or other companies have their apps residing on a central server somewhere. I think that's fine for a subset of the population, but it's not the be-all end-all for everybody, because I want to have all my access to my apps all the time. If there was some mega app that only existed on a could only be done well on a mainframe, or couldn't be done on my phone, maybe I might not be doing that. But for the majority of them, I want them all the time, independent of the bandwidth of the connection that I have. So that's my answer to that one.
Is it true that the phone is still like a black box compared to a laptop, because we get the OS, we get the application to run on it? So is it possible that the next generation we can load the OS or do anything that we do with the laptop?
Oh, come on, you can do it. Okay, NC State student, are you?
Sorry about that.
I'm used to it from now on. I would explain a couple of things. One, all of what you just said isn't true about a laptop. And all of what you said isn't true about a phone. But you're mostly right. The modem part of whether it's a laptop or a phone, you can't get to. And there's good reason for that. From a security point of view, they don't want you lowering the price of your network connection. But also, the code is very complex. The communications code, I've never been a communications expert, and I know now, being in Qualcomm, I never will be. Because it's very complex algorithms that they use. They spend their days looking for optimizations of power beyond what we've been talking about. Because they've got two radios talking to each other, and they have to be extremely efficient. So they've got a lot of sophisticated techniques, and you're not going to get into that modem code. From the point of view of loading an application, you can today write an application and load it on this phone. Can you load a unique OS on the phone? Most of the manufacturers don't want you to do that for business reasons. It's not for any technical reason. The guys in my lab do it all the time. We boot the chip like anybody else who has a phone would boot it, but we know where to stop and go out and get different load. So we can load Linux or with mobile, different variants of Linux on different devices. It's the manufacturer and usually the service provider that say, I want to control what you do with that device. And Microsoft wants to control it too, very much so.
Given the limited frequency space that we're, like, in the United States, we're trying to cram everybody into this small little fraction of frequency. And like that you see over in Europe and stuff, their technologies are a lot progressive, a lot more progressive than ours, so they can do a lot more things. Are we ever going to catch up to that?
Definitely not my area. What I'll say is Asia, Japan, if you want to see what we're going to look like 2 or 3 years from now, go to Japan. They're 2 or 3 years ahead. They were 2 or 3 years ahead when I started at Qualcomm, and I'm assuming that they were at least 2 or 3 years ahead, 5 years before that. Europe has a different, and it's part of the business model, but it's also part of the culture of the people. In Europe, it's also, they're different partly because of the business model. There's much more flexibility with you as a consumer to go wherever you want, whenever you want, pull out the SIM card and go get the next device. In the U.S., Verizon's now talking about being one of the first to actually open up your phone to actually start to do some of that. Do I think it's really going to, are we going to catch up? There's a lot of money tied up in not catching up in those guys controlling things. Technically, it's the same technologies everywhere. So it's not a technical problem, it's a business control problem. It's how you make a lot of money.
So is it supplier to cell phone manufacturers here or in Japan or China? To you, it doesn't really matter. Technically, it's the same thing.
It's exactly the same. There's CDMA technology, the Linux EVDO, best acronym ever invented by a technical company. Technology.
Oh, come on, PC and CIA.
5 meaningless characters. And there's, what do you want to call it, UMTS or the other standards. They're both similar kinds of fundamental standards. The chip that the Snapdragon chip, has the modem for both. There's a few blocks that are different inside the chip, and that's it. And whether it's UMTS in Europe, US, or Asia, it's the same. So it's not a technological thing.
Yeah, maybe I was wrong. I was under the impression that, fine, that the technology is the same, but I need more like in terms of
Spectrum?
Yeah, the spectrum. Yeah. We don't have enough of this piece here.
No.
Like really fit as many people. You drop calls all the time. Like, you
No, that's not what they're doing. There's enough spectrum. What they want to do is, and I'll use the example I remember. They sold me for this laptop that I could connect and get an internet experience, which I'll claim should at least be somewhere around 300 kbps per second, at least that, right? So I can watch my network connection when I'm in that airport trying to do that connection to get my email, and sometimes it might be 300. The best I've ever seen is a megabit. I typically see it go 300, 0, 300, 0, 300, 0, 300, 0. It's how much money they spent on the network equipment, the infrastructure, to allow a certain amount of bandwidth to go through. So it's strictly how much money they spent. It's not that the government said you can only have this much and they ran out. So, there is some of that, but that's not it. That's not why you're dropping costs. It's they don't have an infrastructure to support as many customers as they have. You don't bring it's just not.
Okay, we're running over, so take other questions offline, stand by speaker.
One last thing, there's white boxes in the back corners. I'm giving away mechanical pencils as gifts. You will find the word Qualcomm on these pencils, but you're free to take a pencil.